All right, so here we are in chapter 13. And in chapter 13, we've got the last distribution that we're going to cover. That's the F distribution and one-way ANOVA. Now, previously in chapter 9, our objective was to do a hypothesis test of a claim about a single mean. All right, and if the population standard deviation was known, we used a normal distribution. And if the population standard deviation was unknown, we used a student's t. In chapter 10, we did a hypothesis test about two means. And again, if the population standard deviation was known, we used a normal distribution. And if it was unknown, we used a student's t. But now in chapter 13, we're going to test a hypothesis test or test a claim with three or more means. So say we went from one mean to two means to three or more. The null hypothesis is always going to be that each of those means are equal. And the alternate hypothesis is that at least one of them is not equal. And the distribution we're going to use is the F distribution, which is right-tailed only. You can also use the F distribution for testing a claim of two variances. Okay. So section 13.1 is about one-way ANOVA. So ANOVA stands for analysis of variance. So it uses variances of multiple sample means to help determine if those means are significantly different from each other. So this typically consists of samples with at least a categorical variable coupled with a related numerical variable. So for example, types of sports, that'd be a category, versus grade point averages, that would be a number. So sport is the categorical variable like basketball, baseball, and hockey, and grade point average is a numerical variable representing the grade point average of each player in a sport. So the question we're trying to ask is, are the grade point averages of players in each sport equal or not? Another example would be soil types, just categorical, versus the weight of tomatoes that were grown in different soil types, and weight would be numerical. So soil type is the categorical, so nothing, ground cover, plastic, straw, or compost, versus tomato weight in grams in each tomato plant grown in each type of soil. And, we want to see if the weights of all of the tomatoes were equal, if the mean weight was equal. So there's 5 assumptions to apply to analysis of variance. Okay, trying to scroll down. Oh, too much. So each population sampled is presumed to be normally distributed. All collected samples are independent and randomly sampled. Okay, populations studied are presumed to have equal standard deviations. The categorical variable is called the factor, and the numerical variable is called the response. I'm trying to correct that. Okay. All right, so here's a visual of what we're doing. So let's say one has 3 independent populations and random samples were collected from each population. So the question is, are the sample means significantly different from each other? Okay, so we have two scenarios uh, for figure 1 on the left and figure 2 on the right. So on figure 1, we can see that this top distribution here, this is sample 1 from population 1 with a sample mean, of x bar 1. Population 2, we have sample number 2, okay, and that has a sample mean of x bar 2. And here we have a third sample from a third population, and the center of that sample is x bar 3. So you can see there is a little bit of variation in these sample means. So even though they're not equal, the differences between them are not significant. Okay, so the differences between them are not significant. Whereas over here on figure 2, again, we've got 3 samples from 3 different populations, but now the differences between the samples are greater, okay, and they're great enough that their differences are significant. So one can perform a hypothesis test to determine if the differences in means between samples are not significant or significant to any desired confidence level. Now, the unfortunate thing is that analysis of variance, when you apply it to 3 or more means, it won't tell you which mean caused the problem. Okay, mean or means. Okay, which samples cause the break from to make it from not significant to be significantly different. It'll just tell you if a bunch of samples are significantly different or not. That's about it. Okay. All right. So that right there is the end of 13.1. Let me know if you have any questions.